This is the first section in the vectors chapter, and here we're going to be looking at the equation of a line in 3 dimensions. Now, we're really used to the equation of a line in 2 dimensions, so y equals mx plus c, where m is the gradient. Okay, so it basically tells you what direction the line is going in. And c is the y-intercept. And basically that's just a special point that the line passes through. So a special point the line passes through. We're running out of space again. I must learn to write further on the left hand side so I don't run out of space. Well, the vector equation of a line is written in this form. R equals A plus lambda B. Now, R, A and B are underlined because they're vectors. Yeah, anything you see in bold is a vector. So let's write that down. R, A and B are vectors. The letter lambda isn't a vector. Lambda is a scalar, so it's just going to be something we multiply by. Now, how does this match up with the equation of a straight line? Well, A here is actually any point the line passes through. So any point the line passes through. So it's a bit like the y-intercept. Yeah, but it's not just the y-intercept, it can be any point that the line passes through, this line in 3 dimensions. And B, it's basically the direction the line goes in. And actually what it is any vector parallel to the line. And I call it the direction vector. So it's a bit like the gradient in that it tells you the direction it's going in, and I call it the direction vector. And lambda here, this just can be a number. Okay, so by substituting in different values for lambda, we get different points the line is on, or points on the line, which is R. So R is basically any point, or these are points on the line generated. Let's write that down. So R points on the line generated by different values of lambda. So really my arrow should be pointing to here. Yeah, so we stick in values of lambda, we get values of R and their points on the line. So there's a little diagram over here that sort of shows what's going on. So where are we? So this is the line we're trying to find the equation of. B, can you see that's parallel to the line, a parallel vector? Okay, and we can find these points on the line, they're called R, so it's in reference to the origin. And A, that's another point on the line that it passes through, so they're both going to the origin because it's basically reference to the origin. Okay, find a vector equation of a line which passes through a point A with vector position 3i minus 5j plus 4k and is parallel to that vector. Now it says find a equation because actually there's an infinite number of them. Infinite number of answers. That's because it can be any point that the line passes through and it can be any parallel vector. So let's start by writing down what the general form of the equation of this line is. So R stays as it is. It's like basically like y equals mx plus c. You don't replace y and x with something in the equation. They remain. So R is equal to A. So that's a point that it passes through. And it passes through the point A. And its position is 3i minus 5j plus 4k. Okay, so I could have put any point it passes through, but that's the one we've been given. Plus lambda. We normally use lambda, but it can be any scalar. It could be t, it could be mu. It depends on the question. And b is a parallel vector. So it could be this, or in fact any multiple of this is a parallel vector. So in this bit here, I could have put any parallel vector. And in fact, any multiple of that would have done, i.e. any multiple of 7i minus 3k would have done. Yeah. So that's one way I can write my answer. I may prefer to write my answer as a column vector. So I may prefer to write it like this. 3, negative 5, 4 plus lambda 7, 0 because there's no j, negative 3. Or what I could do is that those two vectors here, so these ones can be put together. So you have like 3 plus 7 lambda, negative 5 plus 0 lambda, or just negative 5, and 4 minus 3 lambda. So another way of writing our answer is like this. Yeah, by putting them together. So 3 plus 7 lambda, then we get negative 5. I could put plus 0 lambda if I wanted to. Don't have to, leave it blank. And then 4 minus 3 lambda. So all of those are acceptable as final answers. So like this, or like this. And it all depends on the question. Sometimes column is more straightforward to use. Sometimes IJK is more straightforward to use. Right, okay, finally, vector equation line which passes through the points A, B with coordinates 4, 5, negative 1 and 6, 3, 2 respectively. Now there's a way that we can work out now the parallel vector. So if it's passing through these 2 points, I can work out what this parallel vector is, basically like this B. Okay, so we can say, so a parallel vector is, now there's 2 ways we can work it out. We can do the second vector minus the first. So that would be 6, 3, 2. So sometimes it's easy to work in columns. Minus 4, 5, negative 1. So that gives me 2, negative 2, 3. Or another way of doing it is just to work out what's the jumps from the first vector to the second vector. In other words, what's the jump from here to here? What's the jump from here to here? What's the jump from here to here? How are we getting from one point to the other? That will give us the parallel vector. So to get from 4 to 6, you go up by 2. To get from 5 to 3, you go down by 2. To get from negative 1 to 2, you go up by 3. Yeah, so just to show you what's happening there, that too is how we get from 4 to 6. Yep. Or this one here was basically how we get from what was it, 5 to 3, and the one at the bottom was how we get from negative 1 to 2. So that's another way of doing it. So we now have this parallel vector, and I can pick either one of these points as a point that it passes through, either the 4, 5, negative 1 or the 6, 3, 2. So my final answer will be R equals a point that it passes through. I'm going to choose the 4, 5, negative 1. Or you could have had the other point it passes through. So remember, it can be any point that it passes through. Plus lambda, using lambda in this case, this parallel vector to negative 2, 3. And just like before, any multiple of this would have done. So any multiple is also correct. So we can leave our answer like that, or we could say, right, let's stick it together and have 4 plus 2 lambda, 5 minus 2 lambda, negative 1 plus 3 lambda. So either one is fine, or you might even go for IJK form. So 4i plus 5j minus k, then plus lambda 2i minus 2j plus 3k. Any one of those is fine. Now we can use any scalar we like. Often you'll see t here as well, or s or mu. So don't think it has to always be lambda. Any scalar. Sometimes in the question they specify, but if they don't, just use t, lambda, mu, s. It's fine. Right, so this straight line has this equation and passes through this point. So that means this: for some value of t, that scalar, for some scalar, the line passes through a, b, 0. So let's find out what this is. So R equals, let's write the equation of the line like this. So 3 to negative 5, and then plus t times by 1, negative 6, negative 2. So what does that mean? So for some value of t, so 3 to negative 5, plus this, the line will pass through a, b, 0. Now what we do, we take each row and we're going to write an equation. So we'll write an equation from that row, an equation from this row, and an equation from the bottom row. This one down here. So let's write those 3 equations out. So the top row we have 3 plus t equals a. Middle row we have 2 minus 6t equals b. And from the bottom row we'll have negative 5 minus 2t equals 0. So this is the one we can find the value of t. So that will be negative 2t equals 5, which means t is equal to negative 5 over 2. Just highlight that. So that now is going to go into the equations we have up here. So this will be 3 plus negative 5 over 2 equals a. So that's like 3 minus 2.5, so a equals a half. Then for this row down here, it's going to be 2 minus 6 times negative 5 over 2 equals b. So that will become 2 minus negative 15, so 2 plus 15 is b, so that means that b equals 17. So final answers: a equals a half, b equals 17. Right, here we've got a straight line, and we've got the vector equation of that straight line here. And then we said show that another vector equation of L is this. Right, so if it's another equation of this line, then it must be, for the second line, we need to show that 8, 3, 1 is a point the line passes through, the one that I've highlighted in red passes through. And also what we need to show is that 3, negative 1, 2 is parallel to 6, negative 2, 4. Okay, negative to that vector, so we'll do both. So if we take the first equation, let's see if we can show that it passes through the point 8, 3, 1. So let's write it in columns. So 2, 5, negative 3, let's stick it all in one bracket, plus 6 lambda, minus 2 lambda, plus 4 lambda. Okay, does that pass through 8, 3, 1? Is there a value of lambda that makes that work? So from the first row, lambda would need to be 1, 1 in the second one, 1 in the third one. Yes, that works. So let's write this down. For lambda equals 1, the line passes through, or it generates the point 8, 3, 1. Okay, so we've done the first bit. So it passes through that point. So that's the point it passes through. And is the second vector parallel? I think it is, yes. So 6, negative 2, 4 is parallel to 3, negative 1, 2, since negative or 3, negative 1, 2 times by 2 equals that. Yeah. Therefore, R equals 8, 3, 1 plus mu 3, negative 1, 2 is another vector equation of the line. Okay, with respect to the fixed origin, the line L is given by that equation. Prove that a Cartesian equation or Cartesian form of the equation of L is that. So Cartesian just means it has x, y, and z. So the first thing to note is that we can replace R, a point that it passes through, with x, y, z. Okay, so it's a Cartesian form of the point that it passes through. So let's do that. So let's put x, y, z instead of r, because that's just a point it generates. Equals this a1, a2, a3 plus lambda b1, b2, b3. Okay, let's multiply out each row, or like write the equations for each row. So the top row is going to give us x equals a1 plus lambda b1. The second row is going to give us y equals a2 plus lambda b2, and the third row is going to give us z equals a3 plus lambda b3. Now let's rearrange these to make lambda the subject, and we're pretty much done. So if you make lambda the subject of each one, so it's going to be x minus a1 over b1. Second one, very similar, y minus a2 over b2. Then the third one is going to be z minus a3 over b3. Now if they're all equal to lambda, they're all equal to each other. So the last step would be that x minus a1 over b1 equals y minus a2 over b2, or minus equals, can't remember what I said anyway, z minus a3 over b3. Now it looks like I've done powers, so let's change that. They're not powers. Stick them down the bottom. 1, 2, 3. So it's been proved as required. Part B, hence find a Cartesian equation of the line with that equation. So first of all, these numbers here represent A1, B1, and A1, A2, and A3, A1, A2, A3, and the numbers here, they represent B1, B2, B3. So we just substitute them into the formula. So we will have part B here, x minus 4 over negative 1 equals y minus 3 over 2 equals z minus negative 2, so you can write z plus 2 over 5. So we've got a line that's got this equation here, and we've got a point P with this coordinate. Show that P does not lie on L. Now, if we're going to do that, what we need to do is to show that there isn't a value of lambda that we can find where we get the coordinate 2, 1, 3. So a general point on a line is going to have this format, negative 2 plus lambda, 1 minus 2 lambda, and 4 plus lambda. So we want to show, is it possible to get this point, 2, 1, 3? So what we do first of all is for each row we write an equation and we find what value of lambda we get. So let's start with the top row. So I would get negative 2 plus lambda equals 2. If I solve that, I'll get lambda equal to 4. So get into the second row down here, we will have 1 minus, and I wrote plus. So 1 minus 2 lambda equals 1, which gives lambda equal to 0 in that case. In the bottom row, we will have 4 plus lambda equals 3. So that will give lambda equals negative 1. Can you see we get 3 different values of lambda? So we cannot generate the point 2, 1, 3 with a single value of lambda. So we can say something like this: since there is not a single value of lambda that solves all 3 equations, 2, 1, 3 is not on L, the line L. Let's move to part B. Now part B says, given a circle with centre P, so that's the point 2, 1, 3, which we were given in first bit, intersects L, the line, at points A and B, and that A has position vector 0, negative 3, 6. Find the position vector of B. So the first thing that we do is we draw a sketch. The centre of the circle is this point P, and its position is 2, 1, 3. So let's write it like that in a column. And we have a line that intersects the circle. So this line is L1, so maybe we'll draw it like that, or not L1, it's just L. It intersects at the points A and B, A and B. Now the coordinate of A we know is 0, negative 3, 6. Let's write that. So 0, negative 3, 6. This one we don't know, let's just call it X, Y, Z. Using the property of a circle, we know that these distances are the same, yeah, because they're both the radius of the circle. So those two dark red lines are the same length. In other words, I could say that the length of the vector A to P, which we can write like that, is equal to the length of the vector that goes from P to B. And we're going to use that property to work out the coordinates of B. So the first thing is, what is the length of BP? Or sorry, AP. So AP, the length of AP, well, the quick way of doing it is to say, right, what's the difference between the X, Y, and Z coordinates? So the difference between the X coordinates is 2, so it's 2 squared. The difference between the Y coordinates of P, A and P is 4 or negative 4. So it doesn't really matter because it's going to get squared anyway. And the difference between the Z coordinates 6 and 3 is 3, so it's 3 squared. This is what it becomes. We don't necessarily need to do the full working. So that's the square root of 16, or sorry, 4 plus 16, plus 16 plus 9. So we get the square root of 29. That is the length of the vector that goes from A to P. That's the same as the vector, the same length of the vector that goes from P to B. Now how do we work out that length? So we work out the difference between the coordinates from P to B. Now how can we write the coordinates of B? It's on the line, so we can write it using the equation, because any point on this line, its equation or its coordinate follows this pattern. So negative 2 plus lambda, 1 minus 2 lambda, 4 plus lambda. So let's work out the difference between this coordinate and this one, and that will give us the length of PB. So the difference between the X coordinates, so this time we can't do it a quick way, we just need to do a subtraction, is, let's do a nice big long square root here, is 2 minus negative 2 plus lambda. So that's the difference between the X coordinates, and that needs to be squared. Plus, now the difference between the Y coordinates, well, P is 1, and we need to subtract 1 minus 2 lambda. Okay, so that gets squared. And the difference between the Z coordinates, well, 3 is P, and the Z coordinate of B is 4 plus lambda, so minus 4 plus lambda, all squared. So my square root sum was almost long enough. And we know that equals the square root of 29. So actually we could square both sides, couldn't we? And we don't need a square root of 29. So I could write down, so the first bit becomes 4 minus lambda. So I'm going to have 4 minus lambda all squared. So I'm dispensing with the square root sign, so that I can write this all equal to 29. The bit in the middle becomes just 2 lambda all squared, and the bit at the end I will end up with -1 minus lambda all squared, and that equals 29. So let's multiply this all out. So we'll have 16 minus 8 lambda plus lambda squared, then plus 4 lambda squared, then we'll have plus 1, then plus 2 lambda, and then plus lambda squared equals 29. So we'll simplify this all out. So we will have, what have we got here? Lambda, 4 lambda, 2 lambda, so 6 lambda. 6 lambda squared, not that, just lambda. Then I'm going to have minus 8 plus 2 lambda, so that's -6 lambda. So -6 lambda. And then for the numbers, I'm going to have 16 plus 1 is 17. So plus 17 equals 29. So from there, let's take away 29 from both sides. So let's do that. So 17 minus 29 is -12. So I'll have 6 lambda squared minus 6 lambda minus 12 equals 0. Let's divide everything by 6. Make it easier, so we end up with lambda squared minus lambda minus 2. That's dead easy to factorize. So that will be a lambda here and a lambda here. So -2 plus 1. Okay, which means that lambda is 2 or lambda is -1. So there's our two values of lambda. Find the position vector of B. Now that means we just substitute lambda in. Now if I substitute those two lambdas in, I'm going to get two different coordinates. One of them is probably going to be A. So if I put lambda equals to 2 into this, that will give me 0. So it's looking like it's going to be point A. And then 1 minus -3 and 6. Okay, so that's the point A. So we use the other value of lambda here to get the coordinate of point B. So we put lambda equal to -1. So we'll have -2 minus 1, so that's going to be -3. Then we'll have 1, and that will become +2, so that becomes 3. And then the last point becomes 4 minus 1, so that becomes 3. Okay, so this is what the coordinate of B is. Right, you should now be able to do exercise 9A on pages 173 to 175. So just remember the equation or the vector equation of a line in 3D is in this form. So this will be a point on the line which we can generate by different scalars. Okay, so by changing lambda, we get different points on the line. A, well, that represents any point the line passes through. The line passes through. And B represents any vector parallel to the line. Okay, and then lambda, okay, that's just a scalar. So that can be any value. So we can use lambda, we could use mu, you see this quite often, S, t, yeah, as our scalar values. So it does mean that there are many correct answers to the vector equation of a line because we can use any point and we can use any parallel vector.